Everyone, and welcome back to another explainer. Today we're diving into a chapter that is going to completely change how you look at foundational math. Seriously, if you've ever felt like the numbers on the page were just, boring, abstract concepts, this explainer is going to flip that right on its head. We're going to see how simply looking out your window, or maybe just organizing the junk on your desk, actually reveals the hidden mechanics of multiplication and division. It is all about learning to see the world through these amazing visual lenses of grouping and sharing.
So here is our roadmap for today's explainer. We're going to kick things off with the moving math problem. Then we'll slide into the power of grouping. After that, I'm going to show you a super clever multiplication trick. And finally, we'll wrap it all up with sharing and dividing.
All right, let's jump right into part one, the moving math problem.
Now, if simple counting worked perfectly for absolutely everything, we wouldn't even need advanced math in the first place, right? But let's look at a really relatable frustration that the chapter brings up. Imagine a character named Ramya. She's staring out her window trying to count the wheels on the traffic going by, and she's trying to do it by adding them up one by one. 1, 2, 3, 4. But wait, the cars are moving. By the time she counts the front wheels, the car has completely zoomed past, and she misses the back wheels entirely. Her method of simply adding them up is totally failing because, well, the real world is just way too fast for basic counting. It is such a brilliant way to represent a problem we've all faced, having way too much information to process sequentially.
Which brings us to our first major solution in section 2, the power of grouping.
Because when the world moves too fast to count things one by one, we've got to change our strategy. Think about the difference here. The slow way is repeated addition. 2 plus 2 plus 2 plus 2 equals 8. I mean, sure, it works, but it's incredibly tedious. The fast way, though, the ultimate shortcut, that's identifying that we literally just have 4 groups of 2, which instantly gives us our multiplication fact. 4 times 2 equals 8. Multiplication isn't just some random set of rules you have to memorize for a test. It's really just a faster, vastly more efficient way to count things that are already neatly bundled together in the world around us.
And what's really fascinating about this is how we have to adapt to what we're actually looking at. Think about a 3-wheeled auto rickshaw compared to a standard 4-wheeled car. When we look out that window, we aren't just seeing generic identical vehicles. We're seeing specific groups of 3 wheels and groups of 4 wheels. This visual distinction actually forces us to change our grouping strategy on the fly. You obviously can't apply a ×4 rule to a group of auto rickshaws. We have to adapt our mathematical lens so it perfectly matches the physical reality of the objects we're looking at.
So the real takeaway here is that by systematically identifying the number of vehicles and then multiplying that by the number of wheels per group, we can solve this moving traffic puzzle in an instant. Let's trace the math. 2 auto rickshaws times 3 wheels each, that's 6. 4 bicycles times 2 wheels, 8. And then the big one, 7 cars times 4 wheels gives us 28 total wheels. By shifting from counting individual wheels to counting groups of wheels, we completely bypass the speed of the traffic. Those cars can zoom by as fast as they want. As long as you can quickly spot 7 cars, the math does all the heavy lifting for you.
All right, let's move into section 3 and look at a really clever multiplication trick.
Okay, so now that we've mastered basic groups, how do we handle things when the numbers get a little too large? The tables of 2, 3, 4, and 5 are usually pretty straightforward. But what happens when you hit the dreaded 7 times table? It is notoriously tricky for people. How on earth do we figure it out if we just draw a total blank and haven't memorized it?
Well, the chapter gives us this incredibly clever hack to break that hard problem down into 2 super easy ones. Step 1, just write out the table of 3, something most of us probably already know. Step 2, write out the table of 4. And step 3, simply add those results together. I know it sounds almost too easy to be true, doesn't it? Let's actually look at the numbers to see how this plays out. Look at how brilliantly this exact logic works. Notice how they add right up. 3 plus 4 equals 7. 6 plus 8 gives us 14. 9 plus 12 equals 21. By taking 2 smaller groups, a group of 3 and a group of 4, and just pushing them together, you've instantly created a group of 7. This entirely removes the anxiety of rote memorization. If you know the smaller, easier building blocks, you can literally construct the larger, more complex tables on the fly. It's just a wonderful demonstration of how flexible numbers really are.
And the best part, this isn't just a one-off parlor trick for the number 7. This is a foundational property of mathematics. You can derive the tricky table of 8 by simply adding together the tables of 2 and 6. The chapter highly encourages testing these observations with your own examples. It also recommends taking physical objects like buttons or little pebbles and arranging them in arrays, neat rows and columns, so you can physically see exactly how a 3x4 grid relates to the numbers you write on the page.
So, everything we've done so far is all about building up, right? Taking small things, grouping them together, and finding a large total. But what happens when we have to do the exact reverse? What if we start with a massive, chaotic pile of things and we need to break it down fairly? That is going to require a shift in how we're thinking.
And that leads us perfectly into our final section, sharing and dividing.
Let's look at how this builds into a totally essential everyday life skill. The chapter uses this great example of two mice sharing a piece of cheese. Honestly, this single idea defines division more clearly than any complex, confusing equation ever could. Division is simply sharing equally. That's it. It's taking a total amount of something and distributing it so that everyone or every box gets the exact same portion. When you split a pizza fairly with your friends, you're doing division.
Let's break down some of the real-world sharing puzzles the text presents. If you have 27 candles and you need to put them equally into 3 boxes, you are dividing 27 by 3 to find out exactly how many go in each box. Or if you have 24 bananas and 3 very hungry monkeys, you divide them to ensure everybody gets a fair share. But look at that last point from the chapter. 8 packets of bindies with 5 in each. Wait a second. That gives us the small pieces to find the total. That's grouping again. The text brilliantly mixes these concepts up to prove a much larger point. Dividing is literally just grouping operating in reverse. If you know that 3 groups of 9 candles is 27, then you inherently already know that 27 candles divided into 3 boxes equals 9. They are literally just 2 sides of the exact same mathematical coin.
So as we wrap up today's explainer, I really want to leave you with this thought. The next time you look out a window or try to organize a big messy pile of items on your kitchen counter, how will you use these visual lenses of grouping and sharing? Because mathematics isn't just trapped inside dusty textbooks, it is the hidden structure of the moving, sharing, fast-paced world all around us. I challenge you to spot the groups and divisions in your own daily life today. Keep observing, keep learning, and I will catch you in the next explainer.